In this video, I'll be going over two important theorems that deal with extreme values. So the first is the extreme value theorem, go figure, and here's what the extreme value theorem says. So the extreme value theorem says that suppose we have f of x and it's continuous on some closed interval, then there's a point in that closed interval at which f of x, or the function f, has an absolute max, and there's a point in the interval at which f has an absolute min. So what does this mean? This just means that if f of x is continuous over some closed interval, we are guaranteed to have both an absolute max and an absolute min. And I think intuitively this probably makes sense. If you think about any function that is continuous, let's say the value of some sort of financial account, like a savings account, if you think of that over some period of time, like from the moment you open that account until 5 years later, somewhere during that 5 years, the value of the account will have a highest value, and somewhere in that interval, the value of the account will have a lowest value. So I think intuitively the extreme value theorem probably makes sense. And we'll see what the implication of this is later on when we look at some examples. Next, let's look at Fermat's theorem, which is named after Pierre de Fermat. He was a French mathematician in the 1600s. He did a lot to develop calculus dealing with very small numbers, amongst many other things. Excuse me. But let's look at this theorem. So what Fermat says is that if f of x has a relative extrema, so a relative max or min at the value x is equal to c, and the derivative of the function at c, if it exists, then we say that that x value is called a critical point for the function. So this is a key term here that we'll be using. And the derivative at that value is going to be equal to 0. So what does this mean? So if we have some function, the graph of which does something like this, and let's say this is C1 and this is C2, so we have a relative maximum value at C1 and we have a relative minimum value at C2. So what we'd say is C1 and C2 are called critical points. Okay, they're called critical points because those are where the relative extrema are. And we can take the derivative at those values of the function. So we can take the derivative at C1 and C2 because the limit from the left equals the limit from the right, and it's continuous at that point, and we don't have a sharp turn anywhere. So we have differentiability at C1 and C2. So those values are critical points. And secondly, the derivative at f prime at c, or the derivative at c, is equal to 0. And this makes sense because we have a horizontal tangent line at each of these values. Okay, so the moral of the story here is that Fermat's theorem tells us that if we have a relative extrema, the derivative at that point is going to be equal to 0. So the derivative at that critical point is going to be 0. So we could just say f prime of C1 is equal to 0, and f prime of C2 is also equal to 0. So a couple points to be careful about here. First is that Fermat only deals with relative extrema, not absolute extrema. I mean, that makes sense from this example. This value right here, that's a an absolute minimum value for this function, but that is not a critical point because, or we don't call that a critical point. Similarly, the derivative at that point does not equal 0. So Fermat's does not work for absolute extrema, only relative extrema. And then we need to be careful because the inverse of Fermat's theorem is not always true. So by that we mean, so up here in Fermat's theorem we said that if we have a relative extrema, so if relative extrema, that means we have a critical point. Okay, so what that means is if we have a relative max or a relative min, we have a critical point at that value, which simply means the derivative at that value is equal to 0. However, so that is true. However, the going the other way is not true. If we have a critical point, that does not mean it's a relative extrema. Okay, so I want to cross that out just to make it clear. And so I'm kind of running out of room and I want to keep everything on this slide, but let's say I have the cubic function. Okay, so here at 0, that's going to be a critical point because, and let's say that this function is g of x. G prime of 0 is equal to 0. The derivative at 0 is equal to 0. However, this is not a relative min or a relative max. So back to what I was saying down here, we have a critical point for the function g of x at 0, but that does not tell us we have a relative min or relative max. So these 2 points I made down here are important for us to remember when we're using Fermat's theorem. So let's look at an example here. It says, find the critical points of the function f of x is equal to x squared minus 1, and all of that is getting cubed, and determine if these critical points are relative extrema. So in order to determine if, or in order to find the critical points for a function, what we want to do is we want to solve the equation f prime of x is equal to 0. So let's take the derivative of f of x. So we're going to say f prime of x, we'll use the power rule and then the chain rule. So we'll say 3 times x squared minus 1, quantity squared, and then we're going to take the derivative of the inside function, so that'll be 2x. So simplifying this, we're going to say 6x times x squared minus 1, quantity squared. So that's our derivative. Okay, and we want to set that equal to 0. So using the product, the zero product property, I can set each factor equal to 0 and solve for x. Okay, so down here I'm going to get x is equal to 0. If I take the square root of both sides in the second equation, I get x squared minus 1 is equal to 0. X squared is equal to 1, so x is equal to plus or minus 1. So the critical points that we have here are negative 1, comma 0, and 1. So 3 critical points. And the only way to really see if these are relative extreme values is by looking at the graph. So the graph of this function looks something like this. I graphed this with technology. And the graph looks something like this, kind of like a parabola that's squeezed together below the x-axis. So we found the critical points, and again, the critical points are telling us where is the derivative of this function equal to 0. So we have 3 locations where that's true. Are any of these 3 values extreme values. Well, a relatively extreme values. Well, -1, when x is equal to -1, and when x is equal to +1, neither of those are relative max or relative min values. But down here, when x is equal to 0, this is a relative min value, because in this interval that I just drew, the value of the function is -1, and that is the smallest value that the function has in that interval. So we'd say no relative max, but we do have a relative min at x equals 0, and the min value